Hi, physics. Mr. Janowski here. This is the first part of the Chapter 8 slides on momentum. So, what do you think of when you hear the word momentum? Because this is a word you've heard before taking physics, so you have some ideas about this word. And think of different examples of objects with momentum. So, when you think of momentum, what do you picture? What kind of thing has momentum? So, yes, this is Chapter 8, dealing with momentum, impulse, collisions, and explosions. So the first thing we did was we watched these different videos. I'll link all these videos in the description of this video. Um, so in these, they were largely, after the Bill Nye one, they were all about things happening, being shown in super slow motion. Because in this chapter, that's one of the things we're going to deal with is what happens when things collide. And we're going to be looking at a very, very tiny, brief instant in time, maybe only a couple of milliseconds long, or maybe even shorter. And the forces that are involved in that period of time are often very, very big. And the objects involved get deformed, put out of shape by a lot in that very brief instant of time. So, symbols and things like that. So, momentum has the symbol P. Again, this is weird. You just have to remember that the symbol for momentum for some reason is P. Momentum is mass times velocity, so P equals mv. The symbol for impulse is J. Again, another weird one. For some reason, we use J for this. Could have used I for this. I understand why we can't use M for momentum, but we could have used I for impulse, but we don't. We use J. So impulse is a change in momentum, meaning J equals delta P. Impulse is the change in momentum, and delta anything is always going to be final thing minus initial thing. So J is also equal to P final minus P initial. Now there's another equation for impulse, and that is J equals Ft. Impulse is force times time. So in the first homework, you're going to have to be, most of it deals with this idea up here at the top, P equals mv. But then at the end, you're dealing with these ideas. J is the change in momentum. So delta P or P final minus P initial. And also J is equal to F times T. And finally, the last equation, this is the equation we'll use for the longer problems at the end, is the law of conservation of momentum. So sigma P initial, the sum of your initial momentum, plus J external, meaning any external impulse that is either giving your system more momentum or taking momentum away, is equal to sigma P final, the sum of your final momentums. So basically, what this means is however much momentum you start with at the beginning, over here, you have to have the same amount of momentum at the end because momentum is one of those quantities in the universe that is always conserved. So again, these are all of the equations we'll deal with throughout this chapter. So here they are, all nice and together all at once. Now the units for momentum are kilograms meters per second, and I'll complain about this throughout this chapter. It has annoyed me tremendously that they never name these after anybody. So every time you need these units, you have to say kilograms meters per second. Um, Although if you look at this formula down here, you could also say Newton seconds, and that would be shorter, but that just somehow doesn't seem right because we're usually dealing with this idea, P equals mv. So yeah, kilograms meters per second. So the book that I dislike says momentum is inertia in motion. I don't like that because if it's inertia, it should have units of kilograms, and it doesn't. It has units of kilograms meters per second. Google's definition I like more. It says it is the quantity of motion of a moving body. So either way you define it, P equals mv. And notice these things have hats. P is a vector because it's wearing a hat. That should warn you that you have to take direction into account when you're dealing with momentum. So a couple of questions. If P equals mv, if momentum is the product of mass times velocity, can two objects with different speeds have the same momentum? And the answer is yes, they can. If the less massive object is moving faster, well, maybe the fact that it has less mass but it's moving faster just exactly cancel, so they can have the same momentum. And the other question, can two objects with the same mass and the same speed have different momentums? All right, well, look at the formula again. P equals mv. So if m is the same and speed is the same, there's the catch, then don't they have to have the same momentum? But in fact, no, because speed and velocity are not the same thing. Speed is the scalar version of velocity. Velocity is a vector. So what that means is you can have two objects with exactly the same mass, and they're moving exactly the same speed, But if they're moving in different directions, their velocities are going to be different, and therefore their momentums are going to be different. So that's how that works. Excuse me. So imagine that we have a speed skater, 38 kilograms. She's traveling to the right at 15.0 meters per second when she collides with the Zamboni. So she's going to hit the Zamboni and bounce off the other way. Now she's going 15 meters per second to the left. So does she have the same momentum before and after the collision? And the answer is no. Because if she was moving to the right, well, we might as well call that, the positive direction and call her velocity positive 15 meters per second. And so she ends up with a initial momentum, P sub I, equal to 570 kilograms meters per second. Whereas after she bounces off, now she's moving left. Well, if right is positive, then left has to be negative. So now she has a final momentum, P sub F, equal to minus 570 kilograms meters per second. So again, the point of this is pay attention to the directions. The direction is going to be very important when you're dealing with momentum. And finally, to review, what is the symbol for momentum? It is P with a hat because it's a vector. What is the equation for momentum? Meaning, what's your basic definition of what momentum is? P is equal to mv. So yeah, when you think momentum, think of that idea first. So we have a name for a change in momentum. It's called impulse. And for whatever reason, the symbol for impulse is capital J instead of capital I. Again, not the way I would have done it, but that's how it's done. And what are the two equations for this thing? Well, J is equal to delta P, and therefore it's equal to P final minus P initial. And also J is equal to Ft. Impulse is equal to force times time. So yeah, you're going to have to mix and match these two formulas and sometimes bring this idea in, P equals mv. And then finally, after whom are the units of momentum named? They're not named after anybody. So the units of momentum are just going to be kilograms meters per second, which takes too long to say, takes too long to write, but that's what we're stuck with. That's what it is. So that's the first part of the slides. Hopefully you found that helpful.